Well, hello, everybody. Mike Norman here at SDSC. I want to talk about Comet, which is our soon-to-be in production HPC system. I'll conclude this presentation with an updated schedule so that you know when this thing will actually be available for you to play with. So the title there is the title of our NSF proposal, and you see the cast of characters down there at the bottom of the screen. And we are partnering with Indiana University on the virtualization part of this project. We call Comet HPC for the 99%, and I'll explain where that number comes from in a minute. But here is the solicitation that we responded to. We were instructed by the NSF to expand the use of high-end resources to a much larger and more diverse community, support the entire spectrum of NSF communities, promote a more comprehensive and balanced portfolio across the seed system, and include research communities that are not users of traditional HPC systems. And, of course, we've been seeing that kind of rhetoric in more recent solicitations. So, this graph shows the 99%. What is shown here in the plot is the cumulative usage as a function of job size in cores on the bottom curve, and cumulative, so that's SUs on the bottom curve. And then the top curve is the number of jobs of a given size measured in cores. And what you see on the top curve is that 99% of all jobs run on Exceed today are smaller than 2048 cores. And then if you look at the bottom curve, you see that about 50–60% of the total SUs consumed are also smaller than 2048 cores. And so we took this as our guidepost when we designed Comet. We didn't want to design a system for full system runs. We wanted to design a system that would cater to the small and medium-sized parallel jobs. So we have some key strategies. They're a little different than what's come before. We do want to grow our user base from of order 1,000 users to of order 10,000 users, and we're looking to gateways as one way to do that. We think of this as a capacity computing system, but still a system that is quite capable up to about 2K cores. We will build upon and expand science gateway efforts, and for the first time, we will provide a virtualized environment as an option for users and application communities who would like to operate their own custom software stacks. And I'll have more to say about that in a minute. Okay, so this eye chart describes the system characteristics. It's about a 2 petaflop system. Dell is the primary integrator. It will have Haswell processors and Mellanox FDR InfiniBand connecting them. About 2,000 standard compute nodes, each with 24 cores. So that adds up to about 47,000 cores in the standard cluster. So the node is dual CPU Haswells, each with 12 cores. The fair amount of memory per node, 128 gigs. And there will also be 320 gigabytes of SSD on each node. So each node is a pretty nice little compute system. There will, in addition, be 36 GPU nodes that will have the same CPUs, but just the Kepler GPUs. These will be the K80. So there will be 2 K80s per GPU node, and each K80 has 2 GPUs, so that's 4 GPUs per node. And then a little later, sometime in April or May, when the technology is available, we'll be deploying deploying 4 large memory nodes. These will be quad socket Haswell nodes with 1.5 terabytes of RAM. Now the HPC for the 99% really shows up in how the system is networked, and so it is a hybrid fat tree topology, which means that within a rack, which is 72 compute nodes or 1,700 cores, within a rack you have full bisection bandwidth, but then we economize between racks with a 4-to-1 oversubscription. And so the whole idea is that we are limiting ourselves to jobs that are 1,728 cores or less. That'll actually be a restriction imposed by the XRAC. Not to say someone couldn't twist my arm and do something larger, but it's really meant for the smaller jobs. The performance storage, which we're getting from Eon, is about 8 petabytes. We're looking at 200 gigabytes per second sustained to that file system. And what we will do is we will take our current Data Oasis Lustre file system, which serves Trestles and Gordon, and we'll repurpose that as what we call durable storage, which will be a second copy of the project directories on the primary file system. So we will be backing up the project storage on the performance storage file system. And then there's a variety of other equipment, gateway hosting nodes, virtual image repository, home directory storage. And this system will be connected at 100 gigs to ESNet and Internet too. Okay, so the next slide is a technical diagram of the network architecture, and the main point here is that it's InfiniBand on the compute side, FDR InfiniBand, but then we bridge to 40 gigabit Ethernet to go out to our Lustre file system. Okay, so the next couple of slides are really directed at you folks, and this is the suggested COMET applications, what we're looking for in the way of applications. So modest core count jobs up to 1728 cores, large memory jobs with 128 gigs per node, that's 5.3 gigs per core. That will be the most memory-rich system time. So this will be great for single node share memory apps as well as MPI apps with a large per process memory footprint. The Haswells have AVX2, so codes with vectorizable loops should run significantly faster there. And then the SSDs, we found from our experiences with Gordon that those node local SSDs are really great for applications that generate lots of temporary files like computational chemistry and finite element apps. More on suggested apps. So the GPU nodes are there basically so that COMET is like a Swiss Army knife. If we have heterogeneous workflows with different stages of different type, and some of those are using GPUs, we wanted to have those available for people. Or if you're just doing, say, computational chemistry, you'd like to have them. So this really doesn't replace Keeneland in scale, but it's a significant capability. The large memory nodes are essential for things like de novo genome assembly or visualization of large data sets. We will be supporting science gateways, and in fact, we will have some servers available for hosting the gateway front ends if needed. But otherwise, we'll be supporting gateways through flexible allocations and scheduling policies that favor rapid throughput. And we do plan to support heterogeneous workflows. And then finally, the high-performance virtualization. This is, we're not virtualizing the entire machine. A virtual cluster will be launched from the job scheduler based on user request. And so you can think of the virtualization as, you know, a software layer that will be available to the application scientist if they want it, so that they can customize their software stacks. And this will be very useful for individuals or communities that have software stacks that are challenging to port to the standard Exceed software environment. All right, so let me now talk a little more about this virtualization, which is a new feature within Exceed. So the enabling technology is called SR-IOV. This stands for Single Root I/O Virtualization. It comes with Mellanox's latest HCA technology.
1 sec, Mike. I'm going to mute the participants here.
Presentation mode is now enabled.
Okay. So the problem, of course, is that virtualization in the past has resulted in significant I/O performance degradation. And the solution is this SR-IOV technology from Mellanox. And what this effectively does is allows the virtual machine to bypass the hypervisor and go directly to the HCA, where various virtual functions can operate, each with their own DMA streams and memory space and interrupts. And what this allows is virtualized clusters operating at near InfiniBand latency and bandwidth. And I'll show some results starting now. So I'm going to start. So I have 4 slides. The first 2 are micro benchmarks, and the last 2 are application benchmarks. And what we did was run some tests on a test cluster we have here at SDSC that has QDR InfiniBand. And we compared both native performance as to SR-IOV performance. And we also compared to 10 gigabit Ethernet, which is what Amazon runs in their cloud. And that, by the way, is available both in native mode and with SR-IOV. So Amazon does have SR-IOV, but only on 10 gig connected clusters. Okay, so if you look at this figure here, there's a lot of lines there. Just look at the bottom line, the blue line, which is the native IB performance on latency. So plotted here is latency in microseconds versus message size. And then the green line just above the blue line is with SR-IOV. And what you see is there's less than a 30% overhead for small messages, and then it trends to about 0% overhead for large messages. So that's real good. And then the dashed lines are 10 gig numbers, and you see, just because of the nature of the connection of the technology, significantly worse latency with 10 gig, about 50 times more latency if you're running in Amazon, with or without their SR-IOV. And then this slide shows bandwidth results. Again, this is a micro benchmark. So now look at the top 2 curves, which is the bandwidth versus message size. And the native is the blue line, and the SR-IOV is the green line, and they're virtually on top of one another. So less than 2% bandwidth loss over the entire range and we can achieve more than 95% of the peak bandwidth. And then if you look at what Amazon does, well, first of all, there's roughly a 4x difference or ratio in bandwidth between QDR and 10 gig. But you don't even realize that in the cloud. We find between 9 and 25x worse bandwidth numbers on EC2. So kind of a nominal number to keep in mind is about we get about 10x more bandwidth on this QDR test cluster than in the cloud. All right, so those were the micro benchmarks. What about real applications? So here's some numbers from WRF. This was a 6-node, 96-core calculation. I mean, we all know WRF. It's an explicit atmospheric fluid dynamics code with nearest neighbor communication. It's a scalable code. And what you see here is the execution time on both the native cluster as well as the SR-IOV, the virtualized cluster. And there's about a 15% overhead. Then Amazon, it's actually not too bad. It's 44% overhead. Well, that's telling you that latency is not too big an issue, I think. That's the way I would interpret that. So it is faster than EC2, but not tremendously so. Here, this is more of an acid test. This is Quantum ESPRESSO. This was a 48-core, 3-node calculation. I'm not familiar with Quantum ESPRESSO, but what I'm reading here on the slide is that it does a CG matrix inversion, and it also does a 3D FFT, which involves a matrix transpose. So there's a lot of non-local and irregular communication here. And we find that the virtualized cluster is, there's a 28% overhead on that, which is not too bad, whereas the Amazon EC2 is just atrocious. Okay, so this is a high-level schedule. We're going to be building and doing component testing in the December-January time frame. Then in February, we'll have some friendly users on, which probably will include some of you if you're really gung-ho to get in and kick the tires. Send me or Richard Moore an email, and we'll put you on a list. We'll be doing our integrated acceptance tests in February, and we hope to have the NSF review panel out as well in that month. And then we're shooting for production sometime in March. And with that, I'm finished. I'll just conclude with the logo cloud of our partners here. And do we take questions?
Yeah, why don't we, I'm going to open up the lines for questions briefly while I load Niall's slides, and then we'll get going with the next talk.
Presentation mode is now disabled.
Okay, so the lines are unmuted if there are any questions for Mike while I upload the next set of slides here.
Hi, Mike. This is Mark at UNC. I was wondering if you could say a little bit more about how people will define their own virtual stacks that they will use. Will users define those, or staff set those up, or how will that work?
Yeah, Mark. Users will define that. We will provide, we'll provide the VMs, but then they have to populate them with their own software.
Will those be Windows and Linux VMs?
That hasn't come up, but there's quite a bit of internal discussion about whether we should provide some standard environments, i.e., different operating system environments. And I think if we see demand for that, we'll do that. The thing I want to stress here is that our focus is on virtual clusters, not virtual machines. And of course, virtual clusters are built out of virtual machines. But, this is not intended to be a VM farm for, a vast number of users. But again, we're going to have to see what the demand is and then adapt to that.
Thanks.
Mike, this is Carol Song from Purdue. I have a question. You mentioned flexible allocations for gateways. What does that mean? Could you give a little bit more detail?
I'm going to let Nancy answer that.
Yeah, I think it's continuing a lot of the policies that we've been using on trestles, Carol. So that's not fully allocating the machine at 100% so that you can get the better throughput, and it's also the ability to adapt to the advances, requesting more CPU that gateways often need because of the unpredictable nature. So I think it's just continuing those gateway-friendly policies.
Okay, thanks.
Sure.
This is Dora Kai from NCSA. I have a question. Are you going to support a database service? Basically,
Support what? Support what?
Support a database service.
Database service. Dora Kai is a database expert in ECSS.
Especially for those open source database like MySQL, like NoSQL, like.
If I can, I think that may be in the next presentation.
Yeah, I think the short answer is no, unless we do something really creative with Gordon I/O nodes, which currently host databases. Gordon is coming up to its end of life in next September, and I have this crazy idea of keeping the I/O nodes as a farm, but that's undecided at the moment. But I would say on the Comet system that I described, no, we do not plan to do that unless it is part of a gateway that is hosted on, some of our equipment.
So with that, I think I'll take that as a nice segue into Niall's talk. I'm going to go ahead and mute the phone lines again. Niall, I know we didn't test this. Hopefully I can still hear you. If not, we'll unmute here. Let's give this a try. And you can just tell me next slide, and I'll advance them for you if that's all right.
Sure, that'll work.
Presentation mode is now enabled.
Can you hear me?
Yeah, great. Go ahead, Niall. Thank you.
Okay, I got a bit of an echo here, so I'll turn down my phone. All right, so I'm here to sort of give an introduction to Wrangler, which is another system that came out of the same call that Comet came out of. And so it's another project that is sort of addressing the same charge of building out to a larger community and addressing some of the, I don't want to call them shortfallings, but places where we could definitely fill in to support what the National Science Foundation researchers need in the computational infrastructure supported through XSEED. So first slide here just sort of shows this is, I'm here talking to you today as the Director of Data Intensive Computing, but everybody else on the slide, those are the co-PIs who were sort of responsible for putting all this together. So I'll take all the glory and they can take all the blame. Next slide, please. So similar to Comet, we were looking definitely at addressing an area where we could support another large community base of researchers out there. And this was about the same time that Wired Magazine came out with this The End of Science Doom and Gloom article, saying that basically, everything is about data, and that's where everything's going to be going. And we don't thoroughly believe that. I mean, we believe computational research is still about computations. But in addition to what's been going on in more the traditional computation environment, is a real need to support a wide range of users, many of whom are not, using systems in XSEED or at scale at this point, to support all of these questions that can be addressed using, big data techniques. And so, in a lot of ways, what the goal of Wrangler was set out from the beginning was to do was to address this area of the computational needs of National Science Foundation researchers. So our strategy here at TAC and around Wrangler is about how we can, what new technologies and how we can push things forward in ways to allow people to do, research that they couldn't do otherwise, but also in ways that are somewhat familiar to them, or using tools that perhaps aren't supportable on systems that exist today, like Stampede and I think Gordon is sort of an exception. There are a lot of things that could be done similar on Gordon, but sort of taking that flag to the next level. If I could have the next slide, please. So some of the science that we're looking at here that we've been doing, but will really be enabled by this new system, are things like what was going on with the Houston Methodist Research Institute here, who brought in over 1,000 different DNA sequences for patients of both a particular form of brain cancer and Alzheimer's, to really improve the coverage of what was understood about these two, terrible brain diseases. And then going through, and not just going through in a high throughput sort of way, but going through doing your data processing, and then coming up with this, as they call it, applied systems biology approach, which involves machine learning and other sort of more big data-y style computations. They were able to go through and not only increase the coverage of understanding of these diseases, but also finding the associations in the progress in the pathways of the evolution of these diseases, to really expose that there is a genetic tracer that comes back through, or markers which come back through and relate these two diseases. So their eventual goal here is to go through and understand how they're related, and then perhaps use existing drug treatments for one disease to see how that impacts one of the other diseases, to try and help stop both of these diseases. It's a great piece of research, but it's sort of a non-standard piece of research as far as an HPC system goes. And so this is one of the aspects of what we're looking to be able to cover with the Wrangler system. Next slide, please. Another important thing we all deal with daily is transportation. And so transportation work, when you are trying to optimize, how traffic flow can be improved, and how we can work within the systems we already have in place, or to improve traffic flow, is a very, very I/O intensive sort of problem to deal with. It's, it's a large graph type problem in a lot of ways. And so we've been working with the Center for Transportation Research folks here to work on some of these problems, and found that many of their workflows, just could not be supported. Computational workflows could not be supported on a system like Stampede, simply because of the I/O rates and the I/O optimizations that needed to be done. And we were able to take advantage of the large memory nodes on Stampede to make RAM disks. And so this is sort of a Band-Aid over the problem of optimizing code and making I/O better, being able to do things in sort of a large shared memory system. But there are many things that we could do with a faster I/O system to enable modeling of this nature. And so this is another sort of problem area that we were addressing with this Wrangler project, was how can we have modeling improved with higher I/O. Next slide, please. And lastly, data comes in all sorts of shapes and sizes. I love this slide because that's an actual picture right there of the box that we got from the Philippines, with a bunch of hard drives with over 3,000 Rice genomes on them. This is part of the 3K Rice Genome project that the Chinese Ministry for Science and Technology has put together. But iPlan is going to be hosting these. And so this is a computationally interesting problem, again, somewhat similar to what was going on with the genetics of disease. But this is to look at the broad spectrum of rice genomes in the world, to understand which genomes grow, or which particular plants grow better in different environments, and identify, perhaps based on their genetic strains, what rice will grow better in some of the areas having trouble producing rice at the levels that are needed to support the current population. And that bottom curve down there shows you sort of how rice production and rice growth has been was up until about 2000, keeping hand in hand. And the demand is going up faster now than production. And so this is something that is really needed for people to be able to address. And it's a large data problem that is going to require a lot of I/O work. And we need to have systems where people can put these things together. Next slide, please. So the goals of Wrangler were to, address these forms of problems and to address the data problems in multiple dimensions. So we're interested not in just, large sequential reads, but being able to support data problems that range in reads and writes for big and small files and read rates in a reliable and secure way. We want to support, multiple forms of data types. We want to be able to work with people in those sort of structured ways that folks who have been working with data are used to in sort of SQL and quasi-structured data and NoSQL databases, but then also venturing into the real big data buzz of unstructured data. We want to have this be fast, not just for the large files, but for random reads and writes. Going across, we heard about the need for some of these in some of the Quantum ESPRESSO and other code bases where small files and read writes are important and are really hindering the ability for larger clusters to be able to compute effectively. We want to support a wider range of applications and interfaces. And when you talk about data these days, especially at conferences, everybody talks about Hadoop, and we certainly do want to support Hadoop. And we want to make one of the system that will be able to, in the throughput aspects, really take Hadoop to the next level. But that's not all that we want to do. We don't want to just limit folks to that particular tool. We want to support also, other what we might think of as less scalable or less traditional languages, such as R and working with GIS data. Databases, both SQL and NoSQL style databases, column databases, graph databases, and many of these sort of forms that don't necessarily fit into an HPC style system. We want to also support data, and to support data, you have to do more than provide a large scratch file system, which is what a lot of people have been used to in the HPC world for quite a while. We want to have, be able to support data over its full life cycle and allow people to not only compute and store their data, but preserve the data and have the data available over the course of the entire project. So we're not looking to just have, temporary storage for folks, but places for people to really manage their results and share and collaborate on those data for years to come. So Wrangler is basically designed with all of these things in mind to make sort of a different sort of system to support all this. Next slide. So the project partners, if you didn't get from the first slide, we have 3 academic partners. Here at TAC, we're the primary system design. We're deploying the system and doing much of the operations. And we're doing a lot of that in concert with Indiana University, who are also hosting a portion of the system, as you'll see in a few minutes, with the replicated file system that we'll have, and also providing us with their expertise in sort of end-to-end network tuning to allow us to get the most bang for our buck in and out for the networking that comes in from other folks, as well as between the 2 sites to help with the replication of the file systems. And we also are working with the University of Chicago, the Globus Online folks, because, for a lot of folks, what it really is about is high-speed data transfer, and that's what, Globus is good at doing. And so we'll be working closely with them, not only to just get Globus Online working, but also to be able to leverage a lot of their publication and other upcoming services that Globus will have to support data compute and data publication. The vendors that we're working with are a pretty short list. If it doesn't say DSSD, it is coming from Dell. So the base cluster architecture, the storage system, the compute systems are all Dell nodes. And then we're working with a company called DSSD, which is now a subsidiary of EMC, but is a company that was started by Andy Bechtolsheim to really build a very novel piece of storage, which is sort of at the heart of what Wrangler is all about. Next slide. So this is sort of a picture of the architecture of Wrangler. Sorry about that. Wrangler at its core is a sort of a very large storage system with what might be considered a smallish HPC system behind it. So we have a 10 petabyte replicated Lustre file system, which is connected by way of a 120 lane non-blocking FDR InfiniBand interconnect to 96 nodes, which are very similar to the nodes that you saw for Comet earlier. They're Haswell-based nodes, 128 gigabytes of memory each, connected amongst themselves and to the rest of the internet by way of a 40 gigabit per second Ethernet fabric. But sort of the special part to Wrangler, once you get past that, is this connection to the DSSD storage. So all 96 nodes of the analytics cluster are connected by way of PCI Gen 3 fabric to a half a petabyte storage system capable of sustaining across the entire cluster an I/O rate of about a terabyte a second, or 200 to 250 million IOPS. And so that's sort of where Wrangler is going to shine, is it's this ability to deal with high I/O rates, taking advantage of both large and small file sizes, as I was talking about earlier. So that's the core of the Wrangler hardware, is pulling all of these things together so that you have a place to store your data, compute with your data, and then work at scale with this high I/O storage system with half a petabyte distributed across all nodes of the compute infrastructure. Next slide, please. Mentioned earlier that we're also working with the University of Indiana in order to provide high availability. There's a second replicated storage system at the University of Indiana, the same 10 petabyte mass storage system, connected again by way of FDR internet to a 24 node analytics cluster. So it will be possible for jobs to run that don't need the flash storage, or for services, databases, other things, which can take advantage of the spinning disk storage that don't need that high I/O rate, to be able to be staged at the Indiana site in addition to the TAC site. And of course, my screensaver kicks in right then. So these sites are connected by way of the 100 gigabit. Cannot type at the same time. There we go. Connected by way of the 100 gigabit internet for replication, but it also provides a connection to two different sites at 100 gigabit per second for people needing to both ingest and retrieve data. Next slide. Mentioned the DSSD storage. At its heart, I wanted to go through some of what this storage system is all about. Contrary to the name, having SSD in it, the real key factor here is that DSSD storage is not SSD based. It's indeed individual, NAND flash storage chips, accessible by way of a RAID structure, which is part of the magic of the DSSD box, but allowing you to connect directly by way of PCI through the switched PCI infrastructure, from the CPU directly to the NAND flash chips. And that's where we're going to be able to really accelerate all of this, is by taking advantage of the parallelism of what we can do with the PCI fabric to the DSSD storage. That direct connection is what is going to allow us to get to this terabyte a second and 250 million IOPS across the 96 nodes at TAC. And at scale, this is roughly 64 times the per node performance of what you get on a system like Stampede, which has a fairly well-tuned parallel file system going for it. This storage system will be presented to users in 3 different modes. It can be presented as sort of a block device for POSIX or other block device type storage. This can be on an individual node basis, or we will also have a Lustre-based system leveraging these POSIX block devices to give us a global parallel file system, taking advantage of both the POSIX nature of Lustre and the distributed nature of Lustre. It can also be presented as a native HDFS file system, This native HDFS file system will not just be layered on top of a block device, but indeed will take advantage of the actual native way that the device works, which is using an object store. So instead of it, they are writing their own, DSSD is providing us with this HDFS driver, which links in with their object store, keyword object pair sort of way of storing things, which is the highest rate, throughput rate that you can get for the system. So with that, with those HDFS drivers, we expect to have one of the highest performant Hadoop file systems available for such a modest sized cluster. As I mentioned, all nodes are connected to all of the storage, and in fact, we will be able to have node-level access controls where we can have particular areas of the flash, limited to being presented to only to particular projects. So we really can get that secure aspect down to being able to have HIPAA-style data hosted in here in a way that's secure. With all the right agreements, of course, and not just, you can't just store HIPAA data on the system, just because we can, but we are able to support projects that will need that level of data access control. Next slide. Flexible environment, so, real-time data ingest at 2 different sites, support for MPI as well as the HDFS file system for various forms of parallelism, a real-time scalable Hadoop environment, system optimized for things like R and Python with parallelism, work that we've been doing with Stampede for a while, taking advantage of that here. Software stack for domain-specific areas, largely based on demand. So we will have our core genomic tools installed, which we know many people will be using. But also, as projects need, we can support folks like the LIGO project or the Large Hadron Collider folks with their software stacks if needed. We need input from people on what software we would like to have on here based on what they need with working with Wrangler. And so if you get in touch with us and let us know, we can work towards getting the proper packages on there. Workflows will be able to leverage the other resources here at TAC because leveraging our global work file system. So you will be able to do work on Wrangler and doing interactive visualization on Maverick, or doing the actual heavy lifting on Stampede and then doing the analytics of some large modeled system on Wrangler. And then support for relational databases and NoSQL databases for various forms of structured and semi-structured data. Next slide. Want to put this up here so that people sort of know what technologies we're looking at. I don't want to read through all of these because we're getting close to the top of the hour. But the boldface things are the ones that we know we're going to have day one. Other technologies are going to be introduced as both demand and time permits to get them onto the system. And if you have particular needs, please let us know what you need, and we can work to get these things going. Next slide. In addition to compute, we will have a data management system leveraging the iRODs, largely, and the Globus Online Data Services to allow people to manage the amount of data that can be processed and worked with on Wrangler. In addition to allowing you to just move and migrate data around, we will also guarantee or work to guarantee the provenance of data as well as the fixity or the checksum, doing checksum checks on data stored in long-term storage to ensure the preservation of the data. We will also log, all access and allow people to get an understanding as how their data is being used and understand, be able to present how they're contributing back into the field of the information by understanding what's going on with their data. Next slide. I mentioned that Indiana will be working with us. We will have end-to-end network tuning, performance tuning, leveraging the internet too, and Globus per sonar tools, and that's a lot of what Indiana is going to be working with us for. But for those who really can't take advantage of either the networks or who just have too much data to deliver practically, there will also be a data dock capability within Wrangler so that we can accept large shipments of drives and migrate the data onto the system for you. Next slide. So Wrangler is currently being integrated, and sounds very similar to what's going on with Comet. We'll be in an early friendly user mode in January, getting folks on there and getting things moving forward. Production is on track for February 2015 to start handling the allocations that are out there and get people going with startups and all those good things. And just to mention, we've been working for a while now with sort of a 16-node prototype system to really understand the capabilities and capacities of this DSSD technology. And it's very promising right now. We're really seeing a very high performance coming off the system, and look forward to integrating all this over the next few months to see where we get to in the end. Next slide. Allocation is going to be a little different on this system than an HPC system. We want to allocate compute nodes, and compute nodes will be, each of the individual Haswell-based nodes with 128 gigabytes of memory. But in addition to that, that puts you in basically, for an hour's worth of time, you would get 1 node hour of allocation on Wrangler. But in addition to what's on the system as the processor, we're trying to, rather than try and carve the system up too much, each node will come with sort of a reserved 4 terabytes storage portion of the flash storage. So balancing out your compute needs is a matter of balancing out how much flash storage you need and then how much processing you need, and coming up with this notion of how many node hours you need to get your workflows done. We intend to allocate this Wrangler more in the style of campaign computing as opposed to job-based computing. So really we intend for people to be able to put their data in the flash storage and compute on it for, say, weeks or months at a time, depending on their needs, to eliminate the data motion problem between the spinning disk and the flash storage. So a lot of what will go into this is more than just figuring out how many jobs you have, but figuring out what you need to be doing with your data over a substantial period of time longer than a few hours. And in addition to the compute allocation, the other allocation is for storage, which is a standard storage allocation as we're sort of used to. Next slide, please. So
Niall, I wanted to leave time for Jim also.
I'm sorry. So if we pop one more forward, then I think I should be done now. So.
Oh, great. Okay, why don't we take questions for Niall? Thank you for a very good presentation at the same time that I switch to Jim's slides. Jim is going to be talking to us about the SuperMic system at LSU. This system has some architectural similarities to Stampede, which I think will be interesting for the user community. The other neat thing about this system is that it was really a campus award that they are allocating 40% of it to exceed users. So that's a huge contribution for us and our user community. Why don't I let Jim go ahead and get started? If there are questions for Niall, if you can send them by chat or email to him directly, we'll have all the speakers' contact information up on the symposium website. Their slides will be up, and also the YouTube recording of the session will be up too. So with that, Jim, why don't you go ahead and take it away?
Thank you, Nancy. I'm Jim Lupo. I'm going to talk about SuperMic today, and there's a bunch of pronunciation stuff that we need to deal with because it's not SuperMic, it's SuperMic because we have a SuperMic system as well. So there's lots of
sorry about that.
There's lots of confusion that goes on around here when you answer phone calls. So next slide, please. Okay, this is the standard heroic picture. 8 of the racks that we have. It's got lots of pretty lights. It's a pretty standard Dell cluster, but it has some interesting features because of the accelerators that we've loaded into it. Next slide, please. So this was funded by an NSF MRI award with matching funds from LSU. We're allocating about 40% of the SUs to Exceed, and so we'll have 6.3 million SUs available per quarter. The way we do that, the SUs are charged by the number of cores that are used, and basically the accelerators come for free. The idea is we want to get people using the system and getting lots of work, apparently cheaply, because they're using the accelerators over using the cores. The system became operational October 1st, and it's now open for general use, so we're expecting a flood of awards from this last XRAC meeting. It's a fairly standard x86-based system. Our measurements show that we've gotten 925, no, not achieved it, but it has 925 teraflops of peak performance. Next slide. Okay, so we actually measured it at 557 teraflops, and that put it about 65th on the top 500 list. The basic system has 2 head nodes. We have 360 compute nodes with dual Xeon Phis, 20 compute nodes with a Xeon Phi and a K20X, and there's 840 terabytes of Lustre parallel file systems. So that's kind of a snapshot view. Next slide, please. The basic configuration is Ivy Bridge processors, so that they have AVX2 vectorized instructions, that sort of thing. We're using FDR InfiniBand on a 2-to-1 fat tree. The management network is Gigabit Ethernet, and we're basically running Red Hat Enterprise Linux 6 on the system. Next slide, please. So it looks like a pretty generic Linux cluster from those characteristics. The head nodes themselves, one of the 2 head nodes has a Xeon Phi, and the other head node has a K20, so that allows people to do appropriate development work on the head nodes, but they can also access the compute nodes via interactive jobs to do the other processing that they would want to do. Next slide, please. The common elements on the compute nodes, we got 64 gigabytes of memory. There's a 500 gigabyte scratch drive on each node. The Xeon Phis are 7120Ps, so they're a slightly newer version than what you find on Stampede. You'll get 61 cores with 16 gigabytes of memory each. 20 of the nodes have one Xeon Phi and the NVIDIA K20X. That particular K20X has 2,688 CUDA cores, but they won't be available to Exceed users. They're being reserved for the project PIs at the university. Next slide, please. So we're aiming it at scalable applications that can handle tens of thousands of cores. At least that's our plan. Molecular dynamics are shown to work pretty well on the Xeon Phis. Things that need adaptive sparse grids, Monte Carlo, Black-Scholes, state of preference analysis, and coarse-grained multi-threading. The system is really designed to let people get some experience, not only with Xeon Phis, but with using multiple Xeon Phis. And maybe from there, once they get used to the system, they can migrate over to Stampede if they need to run really heroic scale jobs on many more cores than we have available. One of the ideas is to look at heterogeneous processing, so people that might be able to split their jobs into fine grain and coarse grain across GPUs and Xeon Phis. And the other thing is we're looking at framework-style computing. So, for instance, we support Cactus here, and people are developing the modules that go into Cactus, which are called Thorns, to use GPUs and Xeon Phis, and that way, once you write a Cactus application and you move to a system, you can automatically take care of these accelerators without doing any additional work. Next slide, please. Okay, so we've got the Xeon Phi set up to support native, offload, and symmetric modes. That does take a little bit of knowledge on the user's part, but we do have scripts that will get you started. Optimal use requires use of the Intel MKL libraries and the Intel compilers and MPI libraries. So you may have to do some porting to get maximum throughput on the Xeon Phis. People who are used to running on Stampede and want to try SuperMIC need to be aware that there are some small differences, and they may run into some slight tweaking issues when they adapt their codes to run on SuperMIC. Next slide, please. Okay, we do have user's guide that can all be reached through our homepage, which is the main site for HPC at LSU. And of course, you can find much of the same information at the XSEED homepages. So with that's a basic overview of the system. And if you have any questions, I'll try to get them answered in the minus 60 seconds I have left.
Jim, thank you very much. I knew it was being a little aggressive having 3 speakers in a single 1-hour time slot, and I appreciate all the speakers working with us to kind of keep the central focus of new platforms coming up. And I'm sorry that you didn't get a decent time allotment. I think Super Mick, I'll have to get myself used to saying that for you, is going to be a really nice development system for folks moving to Stampede as well as a very capable system on its own and operational now. Like you say, I don't have the numbers from the latest XRAC meeting, but I know there were very, very many requests as usual. So I think you'll see a lot of happy users after that allocation.
Well, I think we're ready for them.
Yeah, great. Let me go ahead and unmute the lines here.
Presentation mode is now disabled.
Okay, great. There are some questions that are going back and forth on chat. I wonder if anyone else has questions for Mike Norman had to take off, but questions for Niall or questions for Jim on their systems that you want to just address here on the phone?
This is Amit again. I have another question for Niall. For Wrangler, you mentioned you will be making the storage available on 3 modes. How far along in production that process is? And the reason I ask is we tried to do something on Gordon, and we found that performance was not really good when we tried to, divvy up the storage with multiple users on demand.
Well, that's part of the nice way that you can divvy up the storage in the DSSD, because you really are PCI attached through the switched PCI network. It does actually scale out, and so on that 16-node cluster, that's where we've been sort of scaling out, having on one DSSD device, having multiple block stores mounted up on different systems. And then testing throughputs to those across various systems, and even having multiple paths from an individual system to multiple block devices, in one storage system. And we're finding that it does scale actually fairly well until you saturate the fabric. So we're very optimistic, and that we will be achieving these numbers soon. And I believe that users will not be aware necessarily that they are indeed sharing the infrastructure with the switched PCI environment.
I see. Oh, that's pretty cool. Now, other related thing is, can people ask for persistent allocation? So let's say you're running a web service of some sort. Can they run for an entire quarter?
Yeah, I didn't go into the dedicated services per se. We are planning on hosting dedicated services. So, we will have a MySQL and Postgres dedicated servers running to allow people to put their things into sort of that long-term storage. Similarly, with iRods and other web servers, which will also be hosted on the system, it will be possible for people to have data access through those to enable gateways and other sort of data portals out there.
All right, cool. Thanks.
This is Sergio. Now, is there going to be, like, if you have a dedicated node for yourself for whatever for the year, will that be virtualized in some sense so that multiple users can use the hardware while having the illusion of being the only ones, or does it mean that the thing will actually be in exclusion? My getting a node will be in exclusion of anybody else being able to get it.
Well, we want to allocate nodes for or clusters of nodes within the system to projects. And so it won't necessarily just be for an individual. So you might...
by project. By project.
But, by project. So I'll make that distinction. Right now, we don't have any notion of doing pure virtualization to sort of really, break the system up that way. But we are going to be working I'm very interested in seeing how we can integrate Docker into the system to sort of take advantage of all of this in a shared environment, but to make sure that we can expose inside the the virtualized, not the virtualized, Linux, the Docker I/O images. Actually expose the DSSD in a native form so that we aren't paying any virtualization penalty, similar to what is going on with Comet. That's not our primary focus to begin with. We really are more interested in getting the storage going on as many nodes as we can, but that's sort of on the radar for future enhancements if we have the funding to do that.
Yeah, I'm just, and maybe, this will change over time, but I was thinking primarily of instructions to submitters and reviewers in terms of, like if I wanted to get exclusive access, really exclusive access to a capability, then I would somehow have to prove that I'm more worthy of that than, somebody else who may want it. So, because it really means that somebody else will not be able to use that resource.
Absolutely. And so, part of, I'm thinking that my background's astronomy. There may be astronomical missions that want to have one node that can, really handle the throughput that they need for doing their nightly processing of some of these large-scale surveys. Similarly for labs that are doing, I know the fMRI groups here on campus would be able to do similar work that way. And, at first we want to try it in this mode. We may have to do some multi-tenancy methods where, if you don't need the compute, you can hold on to the storage for a while, and we still sort of charge you for the storage, but somebody else can sort of timeshare on top of that. And those aren't modes that we're looking at right now, but they are things that are sort of on our radar for the future, if and when we find the system is as popular as we hope it is.
Okay, thank you.
All right, thank you. I want to be cognizant of everyone's time and the call now. The speaker contact information will be up on the symposium website, so you can take a look at their slides, contact them after the fact. Sorry, was someone jumping in there? Oh, great. So I want to thank all our speakers today, especially for fitting into a tight timeline. It was really terrific to hear about all the new resources coming online. I think these are going to be really helpful to the user community. And thank you, everyone. Please join us for the next symposium in January.
Absolutely. Thank you, everybody. And sorry for running a little long there, Nancy.
Oh, no. Good topics. Thank you.
Thank you.
Thanks. Bye.
Thanks, Nancy.
Bye-bye.